Okay, welcome back. This is part 2 of our lecture today. And what we're going to be doing now is more specifically addressing some of the impacts that are going to be associated with these changes that we're seeing. Now, your textbook actually divides them up into two kinds of categories here. The physical impacts, as in like changes in temperature and precipitation and ocean acidification and so on. And then like the human and environmental impacts. We're going to just, in part 2 of the lecture here, we're going to focus on the physical impacts, and the third part we'll focus on the more human and environmental types of impacts here. And of course, if we're going to be talking about the impacts of global warming, naturally the main thing we're going to be addressing is temperature. Now, what I've shown here is a diagram that comes from the IPCC 5th Assessment Report, where we're just showing for one of the particular variants of the scenarios. This one happens to be called RPC 4.5. It's one of the A1 scenarios. We are looking at what 42 different models thought that the temperature changes will be, not for like the next 100 years or the next 1,000 years. This is just out to the year 2050. That's not that far in the future. Think about where you plan to be in the year 2050, and you're going to be very uncomfortable with the fact that this ensemble of models, so you can see how each model went off. It's kind of like a spaghetti diagram here. You can see that all of the 42 models, run by 42 different research groups around the world, all of them show warming, and they in fact all show warming in a small range, between about between about a half a degree Celsius and about 2 degrees Celsius between now and the middle of the century. That's a lot of warming. We've already seen about 1 degree Celsius of warming in the 20th century, and now we are adding an additional half to 2 degrees between now and the year 2050. Now, that warming is not everywhere. I mean, how should I put it? It's not evenly distributed. We have that warming, it's more regional than that. And so, like, if we just took, again, this actually is just the warming between, by the year 2035, it's comparing the average from 2016 to 2035 to the previous 20-year period. Boy, there's an awful lot of warming on that diagram. I mean, take a look at that scale there. Those darker red colors there are in the range of like 3 degrees Celsius, just between now and 2035. I invite you to think about where you plan to be in the year 2035, but I'm guessing you don't want the world this much warmer than it is before. But there's a lot of details we can pick up off of this diagram. Again, this is the ensemble across lots of different models here. We're getting a sense as to what is the main result here. I'll talk later about the dots and the cross-hatching and so on in the diagram, but just focusing on the colors there, one thing that you can immediately pick up on is the fact that the warming is greater over land than it is over water. It's a little hard to see on that particular little inset there of North America here, but on another figure in the IPCC report, they showed it more clearly over Europe. Now, I do want to draw your attention, the key is different here as to the scale. They're not saying that it's 3 degrees warmer over Spain, Italy, and so on. It's more like a 1.2 degrees Celsius warmer over there. But you can more clearly see the difference clearly is between land and ocean. And the increased warming over land versus ocean is simply due to the thermal inertia of the ocean. It's not like the oceans aren't going to warm up too, it just takes longer. And remember, this is only out to the year 2035 that we're looking at right here. That, by the way, is the main reason, if you take a look at this diagram here and you say, it seems like there's a lot more warming in the north half than in the southern half, that's simply because there's so much more land in the northern hemisphere than in the southern hemisphere. The southern hemisphere simply doesn't have anywhere near as much land masses as the northern hemisphere does, and therefore the northern hemisphere is going to see more warming than the southern hemisphere is going to. Secondly, I want to draw your attention to another feature in this diagram that we can definitely tell as far as the regional distribution of global warming, and that is that there's going to simply be a lot more warming at high latitudes than there are going to be at low latitudes and so on. And this is mostly due to the so-called ice albedo feedback that we learned about a couple modules ago. As ice starts to melt in those regions, the very high albedo ice that was mostly reflecting sunlight is replaced by darker surfaces like the ground or the surface of the ocean that mostly absorb shortwave radiation. So there's a positive feedback there. Once you start melting ice, you lower the albedo, which causes even more absorption of shortwave radiation and so on. Both this phenomenon of seeing the warming to be more over land than over the ocean, and this phenomenon of seeing most of the warming being at high latitudes versus at low latitudes are simply the continuation of trends that we are already observing. Remember, what we're seeing here is models. What are the numerical models of climate telling us about the climate of the future? Back in early modules in the course, we actually talked about observations, And they were saying basically the same thing, that so far in the 20th and early 21st century, we had seen very much the same sort of patterns. Now, especially in the northern hemisphere, there's going to be differences between the amount of warming in the summer and in the winter. We're going to actually see a much bigger temperature difference and greater warming in the winter than we saw in the summer. If you compare these two panels, where the top one is December, January, February, or DJF, and the bottom one is June, July, August, or JJA, just to use the terminology meteorologists always use. So there's a bigger difference in the temperatures between the winter and the summer, and there's also a bigger difference in the, the wintertime temperatures are going to warm more than the summertime temperatures. There's actually going to be a smaller temperature difference than between the winter and the summer. And in the same sort of way, but not shown on this particular diagram, we're going to see more warming during the night than we see during the day. There'll be a smaller temperature difference between the nighttime temperature and the daytime temperature overall. And the reason for this is a little bit complicated, but in general, keep in mind that we're going to see, the pattern I want you to notice here is that there's going to be more warming at times of day and places and times of year and so on where the temperature is low than in times of day and places and times of year in which the temperature is high. The reason has to do with the fact that greenhouse gases are affecting the long wave radiation part of the energy balance, not the short wave part. And so the changes are mostly going to happen at times when the long wave is what's dominating the energy budget, like at night where there is no shortwave radiation from the sun. Right? During the night, the whole energy balance is being driven by long wave, so changes in the long wave radiation due to greenhouse gases is going to be completely in control of what's happening to the temperature. Same with like in the wintertime, when the days are short and the sun is low in the sky, solar radiation, shortwave radiation, is just a relatively small part of the energy balance at that time of year compared to the greenhouse gases, so, and their effect on the long wave radiation, so we have a bigger effect during the winter than during the summer. If we actually just zoomed into the United States here and look at this diagram from the Environmental Protection Agency, it shows what an ensemble of models in a fairly moderate emission scenario, what they look like. And by the mid-20th century, that's the panel on the left, you can see that there's a lot of warming, but it's principally over the central parts of the United States, not near the coasts, where we are more affected by the maritime air masses that are coming off the ocean, which aren't going to be warming as much, at least not in the first half of the 20th century. You can also see, since they have Alaska on that same diagram there, you can see how there's more and more warming the farther north you go into Alaska. But by the end of the 20th century, in that right panel, you can see that the warming has increased quite a lot. We're getting into, now they're using Fahrenheit on this diagram here, we're getting the central United States up into like 8 or 9 degrees of warming in these climate ensembles. That is an awful lot of warming, and not that far into the future. We don't just change the average temperature, we're changing the distribution of how those temperatures are experienced from day to day. For example, heat waves, or extremely warm days, or whatever. This is a statistic that meteorologists use called TX90P. It's a little bit technical, but basically it's saying how often is the temperature warmer than 90% of the days were in the past. So if there were no climate change, this number should be 10%. 10% of the time, your temperature should be warmer than it was 90% of the time in the past, right? But the temperatures are changing, and in fact you can see that we already, starting in the 1980s and the 1990s and the early 2000s, we're already on a trend upward from 10% of the time seeing these these very warm days. And in fact, now I show you a couple of different emissions scenarios here. On a high emissions scenario, something like A1FI, the fossil fuel intensive scenario, you can see we get to much more frequently are we seeing these unusually warm days. But even in the lowest emissions scenarios, that is a B1 scenario there that's colored in blue. I don't remember exactly which one of the scenarios within the B1 storyline it is. But even in that relatively optimistic scenario where we were investing in green industry and so on, something like 30% of the days are warmer than what we would have seen 90% of the time in the past. So 30% of the time we're seeing these what would have in the past been considered an unusually warm day. That also changes as far as regards to the cold days. Again, this is a statistic TX10P. These names aren't what's important here. But this is a statistic that says how often is it colder than 90% of the days were in the past. When are these unusually cold days? Now again, if there weren't any climate change, we would expect that number to be stuck at 10%. 10% of the time, the temperature should be colder than it is 90% of the time. But, as you can see, in all of our scenarios here, that percentage goes down in the future. It has been going down already in the observations, which are the black part of the line. And then as we move forward into the future, you can see, in the highest emission scenario, which is shown there in red, those very cold days are only happening 1 or 2% of the time instead of like 10% of the time on average. And even in the very optimistic low emission scenario there, the occurrence of these cold days just isn't anywhere near as much as it was before. If I just want to go ahead and talk about what it says actually here in the textbook about this, it says, overall we can have high confidence in the general shape of these predictions. There is of course uncertainty into the exact magnitude of the warming, but it is highly likely that the temperature is going to go up every decade, and that the general distribution of the warming will be in accord with these model predictions. This is solid science. There's not really a lot to argue about. These kind of model ensembles are state-of-the-art science as to how we come to understand the world around us. And I think that the results that they gave us with regard to temperature made a lot of sense with regard to the things we've learned all semester long about the radiative forcings and the feedbacks and so on. This makes sense as to what, in terms of our conceptual models of how all this should work. Let's see if we can apply a lot of the same sorts of reasoning to understanding how global warming is going to be changing precipitation moving forward according to the models. Now, if you think back to earlier modules in the course, it would make good physical sense that the warmer the world gets, the more vigorous our hydrologic cycle is going to be. We should have more evaporation and more precipitation and more runoff and more percolation of soil moisture and so on as the temperature goes up. You might remember the term the Clausius-Clapeyron equation. This is what explains how warmer air holds more water vapor, so more evaporates off the ocean, but then water vapor doesn't stay in the atmosphere, it gets quickly converted into precipitation. And in fact, well, the models, one of the things the models do is compute evaporation. So we can take a look at this change in evaporation, which is a measure of how much the evaporation has increased between now and 2037 in the models. Actually, it's between the average from 1985 to 2005. So it's comparing a recent period to the year 2037. And what we see is that, well, most of this map is colored in blue. And blue means more evaporation and so on. That makes good physical sense. A warmer world should have more evaporation. And so the more evaporation there is, there should be more water vapor in the air. Specific humidity is a measure of the amount of water vapor that's in the air, and we're seeing change in specific humidity. That is the entire world has it in the blues here, where we are seeing an increase in the amount of water vapor that's in the air. And that means that there should be more precipitation. I mean, water vapor doesn't stay in the air. The water vapor has a very short residence time in the atmosphere. It gets quickly turned by clouds into precipitation, and so we should see an increase in precipitation, and that's where the story starts getting a little complicated. I mean, actually, on this map of global precipitation changes between now and 2037, according to the models, well, I mean, if you actually look at the scale there, anything in those greens and blues is more precipitation, and you can see that actually on this diagram, that is where there is mostly more precipitation worldwide. But if you actually look, there certainly are areas where there's less precipitation. Now, I don't want you to get just too wild about that. I mean, notice that the percentages are pretty small. There are places with less precipitation, but we're talking, less than 10% less than before. It only decreased by less than 10%. And I'm going to tell you right here now, those places that are colored there in that kind of yellowy color are all parts of the world where there isn't much precipitation anyway. These are like over deserts and over the subtropical oceans where there's almost no precipitation anyway. But, you see all that cross-hatching on the diagram there, the cross-hatch lines there? That is the notation that the IPCC uses in this document to indicate that the results might not be significant. Okay, it's a somewhat wonky statistical test as to whether or not we should be acting on those, whether or not necessarily we should be trusting the pattern is probably a better way to put it. And you can see that actually almost the entire plot here is covered with that cross-hatching. That's in contrast to those little stippling dots that you might have noticed on lots of these previous diagrams. That means that there is a high confidence that those results are actionable, that you can trust the pattern, not just the times of year, not just the global idea, there's more temperature change. You can actually trust the pattern. Okay, so what they're saying here is let's not get bogged down in like for example, see how there's all that increased precipitation over the Sahara Desert in Africa. Okay, really right there, that's where going to be the most of that precipitation. They're saying don't get bogged down on that pattern. That has a lot of variability from one model to another, and the 42 models they use to make this ensemble and so on. Don't get bogged down in that pattern there. Globally, they're saying there's going to be more precipitation, but that cross-hatching tells us the exact pattern as to where it's going to be, there's not huge agreement. Now, that doesn't change the fact that we can actually learn a lot about the hydrologic cycle from these models. It just means we have to use more sophisticated tools. And I don't want to get bogged down on what all those tools were, but I can tell you that based on the analyses of those models and so on, we can learn, for example, that there will be overall an increase in the amount of precipitation in the tropics, and there will overall be an increase in the amount of precipitation at like high latitudes, like up near the poles and so on. But the exact details of like, it's more over Brazil and less over West Africa, or more over India and less over Southeast Asia, we're not ready yet to make those kinds of assessments of the climate. That being said, though, there are other things we can say too about the distribution of precipitation. And one is, when will the heaviest rainfall events happen? This is another diagram kind of like the ones we saw before about extreme temperature events. This is another wonky atmospheric science statistic called R90P. Again, the names are not important or anything like that, but this is a statistic that says how often will the heaviest rainfall events happen. Rainfall events that are heavier than 95% of the rainfall events in the past. Okay, so again, if there was no climate change going on, then this number would be 5%. We would expect that 5% of the time there would be precipitation that was heavier than the precipitation that used to fall 95% of the time. But we do have climate change, and in fact, notice that whether we're in the high emission scenario or the most optimistic low emission scenario, the percentage of the time when rainfall events happen, they are heavier than the rainfall events of 90% of the rainfall events of the past is going up. So we are getting more and more of our precipitation in the form of unusually heavy rainfall events. And if you look at the black part of the curve, there is actually observations, and you can see that it's been trending up, and in fact it's going to continue trending upward regardless of which of the scenarios we look for. Therefore, extreme precipitation events are going to occur increasingly often according to the models. And that, of course, has implications for things like flooding and so on, okay? The models actually try to also make predictions of things like runoff and so on, so they can understand how often there'll be increased there'll be flooding and so on. In practice, the models are less good at forecasting that, but we know if there's going to be more extreme precipitation events, there necessarily will be more flooding and so on. And so just to use the exact terminology that the book uses there, it says, although we have high confidence in the general predictions at a qualitative level, that is like shifts in precipitation and more rain falling and heavy events, we do have less confidence in the exact details of the changes, such as exactly which regions will see the changes and how big the changes are going to be. So we still have a lot of work to do to understand precipitation and changes in the hydrologic cycle. It's not yet time. It's not that we shouldn't be worried about desertification, the growth of deserts due to global warming. It's not that we shouldn't be worried about flooding and so on. It's that we're not yet sure where those events are going to be happening. Okay, let's talk about some other physical impacts of global warming. How about sea level change? All right, we've learned way back in like Module 2 about all of these changes that we could expect in sea level height associated with both the thermal expansion of the ocean and the melting of grounded ice like in glaciers and Antarctica and Greenland and so on. And as it happens, the models are in pretty good agreement about this, that we can expect about 1 meter of sea level increase between now and the year 2100. A meter? That's like, 3 feet, a little bit more than 3 feet. Do you remember how much sea level increase we've seen so far? It was so far, like since the Industrial Revolution, on the order of like 10 to 20 centimeters. It varied from location to location and so on. So sea level increase is going to be increasing rapidly. This is partly due to committed warming and so on. Now, it's actually a complicated story. Think of 1 meter as sort of the lower bound of this. The models have a fair amount of disagreement among them as to how much ice above sea level, the grounded ice, is going to be melting. if the West Antarctic ice sheet largely collapses between now and the year 2100, there'll be quite a bit more than 1 meter of sea level increase. But just as kind of a baseline as to it will be at least is 1 meter above sea level. And that's extremely bad news because that brings the ocean surface close to the height of a lot of modern infrastructure. Most of the big cities that are near sea level have their sewage systems, their subways, their electrical systems are all very close to sea level, and you have brought the ocean closer to that. Some of that infrastructure is actually below sea level, and it requires pumps and so on to keep it running, and that's all going to get much more complicated as the sea level rises. I mean, just to give you a sense as to how widespread the problem is, here's a topographic map of Florida. And on this map of Florida, anything that's kind of that light pink color is less than 10 feet above sea level, and that green, the bluish color is basically at sea level. So, I mean, now admittedly that black outline that's on there extends a little bit out to sea. I mean, that's not exact, that's the state's legal boundaries, not necessarily exactly where the shore is. But you get this structure. I mean, look at all the area that's in that bright pink in South Florida. There's an awful lot of the world that either will be under seawater or will be under seawater when the waters are unusually high, like during a hurricane or something like that. Oh, that's not good. And that's worldwide. We have, cities at sea level all around the world. That's not good. How about another physical impact? How about ocean acidification? Remember, when we put more carbon dioxide into the atmosphere, that dissolves into the ocean and forms carbonic acid, and that lowers the pH of the ocean. Remember, pH is a measure of the acidity, where lower numbers are more acidic. And if you take a look here, as we look at the historical change, you can see how the amount of the acidity of the Earth's oceans have been decreasing for the last 100 years or so. And you can see that the global oceans are going to get more acidic and have a lower pH. Whether we're on a very low emission scenario or a very high emission scenario, the acidity is going to get considerably worse. And this has very serious impacts for the ecosystems in the oceans. The acidity of the ocean is going to be determining the amount of carbonate ions that are in the ocean, which is about the formation of the corals and the planktons and what other creatures is, mollusks and other creatures in the ocean that pick up calcium and so on to make little shells. And that's kind of the base of the food chain of the ocean. So we're going to have a much less healthy ocean food chain if the ocean continues to acidify, as the models seem to indicate it will be. None of the physical impacts of climate change are good impacts. There's no positive to global change. We're going to talk about the environmental changes in part 3 of this lecture, and that's going to be even worse. But between now and then, we're going to answer a couple quick questions here. Question 3. Where will the greatest warming occur in the 21st century according to the models? A, at high latitudes over the northern hemisphere. B, at low latitudes over the northern hemisphere. C, at low latitudes over the southern hemisphere. Or D, at high latitudes over the southern hemisphere. Where will the greatest warming be happening? Make a choice from those 4 options and get a little feedback before you move on to question 4.